Hello, welcome to the course Excelling with Mathematical Modeling. In my previous lecture, we have done phase plane analysis, which includes phase portrait, the trajectories, and the classifications, mainly the node, the focus, the saddle point, and the center. Now, the question is that all this depends on the eigenvalues and its sign. We have seen that if the eigenvalues are real and negative, then we say that you attend a stable node. Now, the question is why. So, in this particular lecture, I will give a rigorous mathematical proof that when two eigenvalues are real and negative, they will give you a stable node. So, to start with, we take the differential equation and dy dt is equal to some q x y. This is an autonomous system. That means the right hand side does not depend explicitly on t. I take 0, 0 to be the critical point or the equilibrium point. Let C be the path of the system and x equal to ft and y equal to gt, they are the parametric solutions. Of 1, we name it as 1. Now, I need to explain two definitions. We say the path approaches 0, 0, the critical point, as t tends to plus infinity or t tends to minus infinity if limit t tends to plus infinity f t equal to 0 and limit t tends to plus infinity g t equal to 0. We use the word the path approaches 0, 0. If along with that you have limit t tends to plus infinity g t by f t exists, or if the quotient means this becomes either positively or negatively infinite as t tends to plus infinity, we say the path enters 0, 0. So, we have two new terms. One is the path approaches 0, 0 and another is the path enters 0, 0. So, if the path approaches 0, 0, these two limits has to be satisfied, and if the path enters 0, 0 along with these two, this particular condition need to be satisfied. Now, let us come to the definition of node. So, 0, 0 is your critical point of equation 1, critical point 0, 0 of equation 1 is called a node. If there exists a neighborhood of 0, 0 such that every path P in this neighborhood has the following properties. And property 1, that P is defined for all t greater than t0 or for all t less than t0. Number 2, p approaches 0 0 as t tends to plus infinity, and number 3, p enters 0 0 as t tends to plus infinity. So, if these 3 conditions are satisfied, we say the critical point 0 0 is a node. Now, let us come to the proof. So, the hypothesis is that the roots of the characteristic equation are real, unequal, and of same sign. So, we consider a linearized version of the autonomous system, that is Ax plus By, and your dy dt equal to Cx plus dy. So, we assume the solution of this be of the form a e to the power lambda t and y equal to b e to the power lambda t, where your a, b, lambda, they are constants. So, if you assume this to be the solution of this system of linearized equation, you just substitute them and you get a lambda e to the power lambda t equal to a e to the power lambda t plus b e to the power lambda t. And similarly, you will get b lambda e to the power lambda t equal to c a e to the power lambda t plus d b e to the power lambda t. Now, since lambda t is not e to the power lambda t is cannot be equal to 0, you cancel it from the left hand side and the right hand side, and you will get, after simplification, a minus lambda into a plus c into a plus d minus lambda into b equal to 0. So, here your a and b, they are the variables for this equation. I mean, do not confuse with these constants. So, these constants are here, but when you have substitute, now you are solving for this a and b. Let us say they are unknowns. Now, if I consider that a minus lambda determinant b c d minus lambda is not equal to 0, then clearly a equal to 0 and b equal to 0 is the unique solution, and this is known as also the trivial solution. But we are interested in the non-trivial solution, and for that this determinant must be equal to 0. So, you have a minus lambda b c d minus lambda equal to 0 for the non-trivial solution. Now, if you expand the determinant, you get the characteristic equation, which is lambda square minus a plus d into lambda plus a d minus b c equal to 0. And you say let lambda 1 and lambda 2 be the roots of this characteristic equation. We choose lambda equal to lambda 1 and substitute in in this particular equation, let us name it as 1. So, let me rewrite this. We substitute in A minus lambda into A plus B into B equal to 0 and C into A plus D minus lambda into B equal to 0. So, you substitute lambda equal to lambda 1 and obtain the non-trivial solution, which will be of the form x equal to a1 e to the power lambda 1 t and y equal to some b1 e to the power lambda 1 t. So, basically you substitute lambda equal to lambda 1 here and obtain some solution of a and b, which you name it as a1 and b1. And once you get it, you substitute it back, a equal to a e to the power lambda t, that was the form of the solution. So, you substitute in place of a, it is a1, which is obtained from this equation, and the value of lambda is lambda 1 t. So, that is how you get this particular expression and this particular expression. In the similar manner, if you put lambda equal to lambda 2, you will get the solution to be x equal to a2 e to the power lambda 2 t, y equal to b2 to the power lambda 2 t. So, again in the similar way you substitute it here and get another solution, which you name it as a2 and b2 for lambda equal to lambda 2, and you substitute back here and you get again this solution. So, here your a1 b1 a2 b2, they are called definite constants. These solutions are linearly independent. So, your general solution will be of the form x equal to some c1 a1 e to the power lambda 1 t plus c2 a2 e to the power lambda 2 t, and similarly y equal to b1 c1 b1 e to the power lambda 1 t plus c2 b2 e to the power lambda 2 t. So, this is now the general solution of the differential equation dx dt equal to ax plus by and dy dt equal to cx plus dy. Let me rewrite the equation. X equal to c1 a1 e to the power lambda 1 t plus c2 a2 e to the power lambda 2 t, and y equal to c1 b1 e to the power lambda 1 t plus c2 b2 e to the power lambda 2 t. Here c1 and c2, they are arbitrarily constant. Whereas your a1, b1, a2, b2, they are definite constants. Now, let us choose C2 equal to 0. So, if you choose C2 equal to 0, you get x equal to C1 a1 e to the power lambda 1 t, y equal to C1 b1 e to the power lambda 1 t, and if I divide, I can get y by x equal to b1 by a1. Your lambda 1 t will cancel. This is one set. Again, if I choose C1 equal to 0, I will get x equal to C2 a2 e to the power lambda 2 t and y equal to C2 b2 e to the power lambda 2 t. Then again y by x equal to b2 by a2. This is my another set. Now, I say let lambda 1 and lambda 2 are negative. So, by taking that, I will show that this represents a stable node. Now, say I name this set as 2 and this as 3. So, if your C1 is greater than 0, so if your C1 is greater than 0, the solution which is represented here, they will consist of a half straight line, which is of the form y equal to b1 by a1 times x with slope b1 by a1. And if your C1 is less than 0, then again you will get the other half of the straight line, which passes through the origin, as you can see here, and with the slope b1 by a1. So, the two paths enters 0 0 with slope b1 by a1. So, what you are actually getting is that you have something like this. So, one half of the line is entering the origin like this, and the other half is entering like this. It is the same line. This is for say C1 greater than 0, and this is for say C1 less than 0. And the properties which you need to see is, we have taken x equal to ft and y equal to gt. So, if I express that this is my ft and this is my gt, then I need to show limit t tends to plus infinity ft, which will be limit t tends to plus infinity C1 A1 e to the power lambda 1 t. And since I have taken lambda 1 t is less than 0, so this will be equal to 0, because there will be an exponential decay. It's more clear if you can just put a negative sign and you can just visualize as t tends to plus infinity, this becomes less and less and ultimately goes to 0. In the similar manner, t tends to plus infinity gt, that is this will also be equal to 0, which means the path approaches 0 0. Along with that, if you now show that limit t tends to infinity gt by ft, which is equal to limit t tends to plus infinity. So, gt by ft from here is b1 by a1, and this will give you again b1 by a1. So, a constant value. So, this implies that the path enters 0 0. So, both the properties are satisfied, and we get that when C2 is equal to 0, you get when C1 is greater than 0, you get a half straight line, and C1 is less, you get the another half, and together they consist of this particular straight line. The same thing holds for C2, that if your C2 is greater than 0, so if your C2 is greater than 0, in that particular case you will get your x equal to C2 A2 e to the power lambda 2t, y equal to C2 B2 e to the power lambda 2t, and your y by x equal to B2 by A2. So, if C2 is greater than 0, you get a half line, and if C2 is less than 0, you get another half of the line. Both are approaching and entering the equilibrium point 0 0. From here you can see that since lambda 2 is less than 0, limit t tends to plus infinity, this is your ft, this is your gt. So, ft is equal to limit t tends to plus infinity C2A2 e to the power lambda 2t. Since this value is negative, this will be 0. With the similar logic, you will get limit t tends to plus infinity gt also equal to 0. And if you want to see limit t tends to plus infinity gt by ft, that is limit t tends to plus infinity y by x, which is b2 by a2 from here, and it is constant, gives you a finite limit. So, that means it approaches and enters the point 0, 0. So, these two are rectilinear cases. By rectilinear cases means when you get a straight line. Now, let us move to the non-rectilinear cases. Suppose you have C1 not equal to 0 and C2 not equal to 0. In that case, what you will get? So, if I write the equation one more time, this is C1A1 e to the power lambda 1t plus C2A2 e to the power lambda 2t, and y equal to C1B1 e to the power lambda 1t plus C2B2 e to the power lambda 2t. So, here lambda 1 less than lambda 2 is less than 0. So, both lambda 1 and lambda 2 are negative values. So, if we now check limit t tends to plus infinity, suppose again this is f t and this is g t. So, f t, that is limit t tends to plus infinity C1 A1 e to the power lambda 1 t plus C2 A2 e to the power lambda 2 t. So, this is, because this is negative, it is easy to visualize if you directly put a negative sign here. So, this goes to 0, this goes to 0, and you are getting this value to be 0. So, why we are doing this? Because in the definition of the node, if you recall, it says that the path approaches 0, 0 and the path enters 0, 0. So, these two property will ensure that the path approaches the equilibrium point 0, 0 and C1 B1 e to the power lambda 1 c plus C2 B2 e to the power lambda 2 c. Again with the same logic, this becomes 0. And the third property, which says limit t tends to plus infinity gt by ft. If this also gives you a finite limit or tends to plus infinity or minus infinity, then we say that the path enters 0, 0. So, here if we find this y by x, that is C1 B1 e to the power lambda 1 t plus C2 B2 e to the power lambda 2 t divided by C1 A1 e to the power lambda 1 t plus C2 A2 e to the power lambda 2 t. So, I take this C2 e to the power lambda 2 t common, and I will get C1 B1 by C2 e to the power lambda 1 minus lambda 2 into t plus B2. So, you take this and this common, and from here also this and this common. So, this C2 will be cancelled. So, if I elaborate this, I will be getting C2 C1 B1 by C2 e to the power lambda 1 t by e to the power lambda 2 t, here also e to the power lambda 2 t plus B2. Similarly, I take here also C2 e to the power lambda 2 t common, and similarly you get an expression, this and this cancels and you are left with this. So, this is exactly what I am writing here. This divided by C1 A1 by C2 e to the power lambda 1 minus lambda 2 into t plus E2. Now, as t tends to infinity, so this is equal to limit t tends to plus infinity. So, this is equal to limit t tends to plus infinity. So, you can see that this tends to 0 because your already you have taken that lambda 1 is less than lambda 2. So, lambda 1 minus lambda 2 must be less than 0. So, as t tends to plus infinity, this goes to 0, this goes to 0, and the limiting value is a2 b2 by a2. So, now this ensures that the path approaches 0 0 and this ensures the path enters 0 0. So, for both the rectilinear case and non-rectilinear case, we see that the path approaches 0 0 as well as the path enters 0 0, and by definition of the node, and hence this will 0 0 will give you a node when both of the eigenvalues are negative. And if you draw the figure, you will get something like this. The first one is a straight line for the rectilinear case. The another one is also another straight line, and the rest are the non-rectilinear paths. So, you can just draw something like this, 1, 2, they are entering, 1, 2, they are entering, and hence this represents a node, and as you can see that they approaches and enters the origin 0 0, hence an asymptotically stable node. So, when your lambda 1 and lambda 2 are less than 0, you see that the path represents a the trajectories, they becomes a asymptotically stable node about the equilibrium point 0 0. If your lambda 1 and lambda 2 are positive, both are positive, then everything remains the same, but only thing that you have to derive the whole thing when t tends to minus infinity, and you will see that all the paths, whether it is rectilinear or whether it is non-rectilinear, this will approach and enters 0 0 as t tends to minus infinity. And because it tends to minus infinity, the diagram will be exactly the same, only the direction of the arrow will change. So, in this particular case, this is the straight line and this is the straight line, your arrow will be outwards along with the paths, and this represents a unstable node. So, with this I assume that you get a clear idea that when two eigenvalues are real and negative, they will represent a stable node, asymptotically stable node. A similar way you can prove for a spiral or for a saddle point or even for a center. In the next lecture, we will be taking some typical examples involving this Lyapunov stability. Till then, bye bye.